I have a fully non-math related question for either of you.
Mhm.
Is there like a super awesome place around here to get a burger?
I actually don't, there was just like a quick, like, one that's easy, like fast food, one that's like really, really delicious. 'Cause I don't,
I'll take the name of either, but today I'm looking for more quick, but.
yeah, I don't really know. I know that there's like, I usually just go to Chick-fil-A after
Okay.
class.
You said you want what?
Like a burger,
Oh, the best place where I usually go is Five Guys.
5 Guys.
Yeah, they have a very nice one.
I would suggest Five Guys as well. That's up by, towards the Chubbuck area. And then I go see us in the Firehouse Subs, the Costco right there.
I'm not from the area, so I don't know too much.
Yeah,
Like,
Five Guys, I think. is the best.
I have to drive in from Twin Falls every day, so.
Yeah, I just went there a few months ago, so.
You're still figuring it
I'm
out.
still figuring it out. Get to know a few places, but, you know, I haven't gotten out much since actually recently, since the weather got better. I've gotten out more. But
So if you don't see me during class, it's probably because I'm watching your videos instead from home, so I don't.
Okay,
be hours
so-
driving.
I also figured out there was an issue with the document camera actually.
Yeah,
So that is why I was not recording the class. So they fixed it like today. So you guys will be able to
kind of hoping.
see the YouTube.
I have calculus 2 in the morning too, so I'm like, I have to come for that anyway. So I'm hoping that I can manage it so that.
Yeah.
Maybe like
And then,
a day or two a week, I don't actually have to drive out here, because I
Yeah.
feel like I'm losing a lot of study time just in driving.
Yeah, driving to and fro is like, it's almost 2 hours, right?
Yeah, it's about 2 hours each way.
Yeah.
So it's a total, like I'm losing between 3.5 and 4 hours.
4 hours, yeah.
in My day just in
That's a lot.
driving, it's a lot. Especially 4 days a week, it's like if it's like Tuesday, Thursday, or Monday, Wednesday, Friday, it's not so bad, but.
when I started college, I first went to the University of Nevada, Las Vegas. I lived way on the edge of like the city. So it was about a 45-50 minute commute in traffic across the 95
Yeah,
down to near the strip of Las Vegas. I went to a lot of audiobooks.
Yeah.
in, first year and a
and that's
half.
kind of what I'm doing, I'm going through a lot of audiobooks and. I actually think this weekend, I found some like online lectures about Calc 2 and linear algebra, and so I think what I'm gonna do is watch some in advance and then listen to the lectures while I'm driving, so that it like,
Good help.
Yeah.
Comes up, man.
Living dream,
Yeah.
straight from work. Sorry if I get your classroom dirty.
Okay, so we'll have a worksheet tomorrow. So that'll be 10 minutes, the last 10 minutes.
Open notes.
Yeah, 50-50.
If you only have 10 minutes though, your notes aren't gonna do you that much
Yeah,
good.
okay, so all that.
I can't read that many notes.
Yeah. So it will be very easy. Actually, I'll tell you which the one which I'll give it to you so that you can go home study. Yeah, so the solution here. So the last question that we did was where we got a unique solution. Like we were getting one solution which was actually unique. So now, in that case, in the previous one, since we were getting the unique solution whereby there were no free variables actually. But for this, we'll see that we'll get free variables. So So we follow the same steps that we did. So the steps are, we write this one in augmented matrix form. So whereby we get 1 minus 7, and then x3 is 0, and then 6, and then the constant term is 5. So we have 0, x2 is 0, x3 is 1, and then minus 2, and then minus 3. And then lastly here, minus 1, 7, minus 4, 2, and 7 there. Okay. Now, we now reduce the second one has already been reduced. So we reduce the third one. So to get the new R3, then it is R3 plus R1, R3 plus R1. So we retain minus 1, 7, 0, 6, and 5, and then 0, 0, 1, minus 2, and minus 3. And then now minus 1 plus 1 is 0. 7 plus minus that is 0. And then minus 4 plus 0 is minus 4. 2 plus 6 is 8. And then finally, 7 plus 5 is 12. Okay. Now, if you look at this, so we have our pivot position here. So we should also have our pivot position here. So again, we need to reduce this one to 0. So the next one now is to get the new R3, then is R3 plus 4 R2, which will now be 1 minus 7, 0, 6, and 5, then 0, 0, 1, minus 2, minus 3, and then 0, 0, 0. And then 8 minus that is 0 again. 12 minus this one is what? Is 0. Okay. So if you look at that, this is our pivot position, and this is also our pivot position. So so this is in echelon form. We have done it in echelon form. Now you need to do it in reduced echelon form. So above the pivot position, is it a 0? Which is 0, right?
Yeah. Yep.
So it is a 0. So that is good. So therefore, you can say now our basic variables are x1 and what? And x3. Our free variable x2 and what? And x4. X2 and x4. So then our new linear system here will now be x1 minus 7x2 plus 6x4 equals to what? Equals to 5. And then the next one here is x3 minus 2x4 equals to minus 3. So we want to make this one x1 the subject, so we take the other ones to the other side. So x1 equals to 5 plus 7x2 minus 6x4. And then x3 equals to minus 3 plus 2x4. Now, our solution set. Let me not go into that. We'll do it later. So therefore, in this case, we can see that x1 can be equals to these values for what? For any x2 and what? And x4, right? For any x2 and x4. So therefore, x1 can be any value for any x2 and x4, and also x3 can be any value for any x4. It can be 0, it can be any value. So therefore here, then if we have the free variables, then we have infinitely many number of solutions here, because you can put any value there. So you can put 0 for x2 and x4, and then you can still get, you can put 1, you can put minus, you can put, so you can leave it like that. So that is our solution. So for any x2 and x4, right? Good. Right, let's come to the next one, number C. We have x1 plus 3x3 plus 5x3 equals 7. 3x1 plus 5x2 plus 7x3 equals to 9.
And it's supposed to be 3x2.
The top row, you have 2 x3s.
I have started earlier. 5x1 plus 7x2 plus 9x3 equals to 1. Okay, following the same steps. So the solution. So write this one in augmented matrix form, which is 1, 3, 5, 7, 3, 5, 7, 9. And then 5, 7, 9, and 1. And then follow the same procedure. Follow the same procedure. So the new R2 will now be R2 minus 3R1. The new R3 will be R3 minus 5R1 minus 5R1. So when you reduce that, then what you should get is 1, 3, 5, and 7. And then you get 0, minus 4, minus 8, and minus 12, and 0, minus 8, minus 16, and minus 34. Minus 34. So when you reduce this one, actually this is similar to what we did previously. So when you reduce this, the last one, the new R3 will now be R3 minus 2R2 minus 2R2. So what you get is 1, 3, 5, and 7, and then 0, minus 4, minus 8, and minus 12, then 0, 0, 0, and finally minus 10. So without even continuing from there, then the last one is what? Contradictory. So the last row is contradictory. So therefore, x0, x1 plus 0, x2 plus 0, x3 is equals to what? Minus 10, which is not what? Not consistent. Not consistent. So if it is not consistent, then there is no solution there. So we have no solution. Since the last row is contradictory. Contradictory. Okay, any question up to that? Okay, let's write the summary here. 2.3 summary. There are exactly 3 possibilities for the solution sets of a linear system. And we have actually seen them from the examples that we had. So number 1, the linear system has no solution if there exists a contradictory row in an echelon form of the associated augmented matrix. Just like the last example. So there is no solution if we have the contradictory row. Number 2, the linear system has a unique solution if it is consistent and does not have free variables. And then number 3, the linear system has infinitely many solutions if it is consistent and has a free variable. Has a free variable. Okay, so this one summarizes the 3 examples that we had. So this is what I'll give you tomorrow for your worksheet. So I'll ask you worksheet. So this is actually what I'll give you tomorrow. So we have x1 plus 2x2 equals to h minus 2x1 plus kx2 equals to minus 8 equals to minus 8. So I want you to determine all possible values for the parameters h and k in the following linear system, so that it has, number A, no solution, number B, unique solution, and number C, infinitely many solutions. So this is what you will do tomorrow for your workshop. Okay, any question after that? Any question? Okay, let's now come to the vector section 1.3. 1.3, the vector equations. The vector equations. I think this one is the easiest section that we will do. And we'll actually be dealing with the vector addition and vector multiplication. So it will be so easy. So we'll denote the sets of all real numbers by R. So the set of real numbers will just denote it by R, the capital R. And elements in R, we can say A to be in R. And this A is actually a vector. A to be in R. That A is a vector. So this says that A is in real number, which is R. A is in R. It's in R. This is a vector. Okay, let's look at definition 1.1. Definition: an n-dimensional vector with real entries is an n by 1 matrix, which we can write as A, the capital the A equals to A1, A2, all the way to A, which we can also still write as A1, A2, all the way to AN, and we use the parentheses. We can write it like that. So that is a vector. And these vectors, this A1, A2, up to AN, A1, A2, all the way to AN, are elements of real numbers. So they are real numbers. Okay. So they are real numbers. So if we have n number of real numbers there, we can actually say that the sets R and then raised to n, R and then raised to n of all n-dimensional vectors with real entries is called the n-dimensional vector space. So this Rn, where n are the number of real numbers here. So it is called the n-dimensional vector space. So this is a vector space, n-dimensional vector space. If all the entries are zeros, then we can actually call it 0, 0, 0, 0, 0 vector. If the entries are zeros, so we can say if all entries are 0, then it is a 0, which you can write as 0, and then we can just put it like that, 0 vector. Now let's come to the next section, which is the operation. Operations. Now, if we let A to be equals to A1, A2, all the way to AN, and our B to be equals to B1, B2, all the way to Bn. And these are elements in the n-dimensional vector space. Then, and also C, which is an element of real number, and C is our constant. So this C is a scalar. So this is a scalar. The C is the scalar. Then, number one, vector addition. If we add vector A plus vector B, then it is the same as adding this A1, A2, all the way to AN, plus B1, B2, all the way to Bn, whereby this is equals to A1 plus B1, A2 plus B2, all the way to AN plus Bn. If we multiply by a constant, if we multiply by that scalar, which is C multiplied by the vector, then this is the same as C here outside, A1, A2, all the way to AN, which is the same as putting it inside, which is CA1, CA2, all the way to CAN. CAN. Then number three, so this is number one. Number two, this is the scalar multiplication. And then number three, negative vector. If we have a negative vector like that, then this is similar to -1 and then A. And this -1 is a scalar. So that -1 is a scalar, which is just similar to number C there, number B, I mean, number 2. So, and this is the same as -1, and then A1, A2, all the way to AN, which is similar to -A1, all the way to -AN. A1, all the way to -AN. So it's similar. And then finally, number 4, if we subtract, like vector subtraction, then if we subtract A minus B, then this is similar to A plus minus B. A plus minus B, which is the same as A1, A2, all the way to AN plus -1, B1, B2, all the way to Bn, right? And this is similar to A1 minus B1, A2 minus B2, all the way to AN minus Bn. AN minus B. So the most important operation that we will be working on is the vector addition and scalar. So these are actually just like the most important is the vector addition and vector and scalar multiplication. Okay, example number 1. if we let A, the vector A to be equals to 2, 3, and 5, the vector B to be equals to -1, 0, and 2, and C to be equals to 10, then find A plus B, CA, and also find A minus B. Find A minus B. Okay. Now, solution. So A plus B is similar to 2, 3, 5 plus -1, 0, and 2, which is equals to 2 minus 1, 3 plus 0, and then 5 plus 2. And this is equals to 1, 3, and 7. C multiplied by A, and this C is equals to 10 multiplied by A. Then this is the same as 10, 2, 3, 5, and this is equals to 10 multiplied by 2, 10 multiplied by 3, 10 multiplied by 5. And this is the same as 20, 30, and 50. And then finally, A minus B is the same as 2, 3, 5 plus -1. -1, 0, and 2, which is similar to 2 plus 1, 3 minus 0, and then 5 minus 2. This is equals to 2 and 3, 3 and 3. Okay, any question after that? Okay. Now let's see how we can geometrically draw this vector addition and scalar multiplication and subtraction as well. Now, if number 1.3, let's say this is geometric interpretation. If we let A to be equals to A1 and A2, B to be equals to B1 and B2, and all these are in R2. So these are in R2. So there are two of them. There are two entries there. So they are in R2. So there are two entries there. So R2. The other one was Rn. So there are n number of entries. This one is R3. So the entries. Now, if we add, like, for the vector addition, then to draw this, then if we have, we put this one as x1 there, and this one is x2, right? Then for the vector A, actually the vector is in the direction. That direction is starting from the one origin, 0. So that origin is 0, 0 up to the point A1. So from 0 to the point C, that direction. That's a direction. A vector has a direction. If you're doing engineering, I think you know this here. So you're starting from point to the other one. So if we have A to be A1 and A2 there, So we can take this as A1, which is in X, and then A2, which is in Y there. So A1 and A2, we can put it over here. Okay. So it is going to that direction. Up to here. So this is our what? A. So that is our A. Then if we have our B, then we can put it up here. Our B to be starting from the origin to, let's put this one to B1. So let's take this one as our B. So we can take this one as B2. Take this one as B1. Take this one as A1. Take this one as A2. Then if we add the two vectors here, then basically it start from the origin. So we add. So if we add these vectors, then it will go that way. So, and this one is A plus A. So basically, it will just be like that. Okay. So then this will be A2 plus B2, and this will be A1 plus B1. Now, if we multiply by the scalar, and we can take here and C to be the element of real number. C to be the element of real number. Then if we have the scalar, this is the scalar multiplication. Now, if we take x1 here and x2 here, if we take our C multiplied by A, then if from here up to here is A1 and this is A2, then if we multiply by the scalar, then this will just extend that way. So it will just extend that way. So this will be CA1 and then CA2, CA2. So that's extended. Then finally, if we subtract, if we take this one S, if we just take it like up here, we take this one as A1 and here as A2, and then take B to be here. Take this one as B2 and here as B1. Okay, B1. Okay. Now, if we subtract, what happens? If we subtract, what can we see from here? So if we subtract A1 minus B1, A1 minus B1. Okay. So which one is bigger here? A1, right? So so A1 is bigger than B1. Okay, what about A2 minus B2? So B2 is larger one. So it will be what? Negative. It will be negative. So it will now come to this direction here. To that direction. To that direction. So this will now be
Wouldn't it be down?
It would be down.
No, so we
be like in the
will
fourth
just do the
quadrant.
opposite direction. So we'll just take,
Yeah, but A1's still gonna be positive.
we'll take B minus A. We'll take B minus A.
Okay.
So we will take B minus A. So if you take B minus A, then it will be B1 minus A1, right? B1 minus A1. And which one is bigger? A1. So it will go to this direction.
Why would it go to that direction?
So do B minus A instead of A.
So B minus A. So B is small. And A is big. So if you say if this one is 2 and this one is 4, so it will be 2 minus 4, which will be minus 2.
But if it was A minus B, it's
Yeah.
in the fourth quadrant.
Yeah, exactly. So it's B minus A. So it
Okay.
so it will come here. Now, B2 minus A2 will be what? Will be in the positive direction. So it will just be up here. So that is subtraction. Vector. Okay, any question after that? Good. Now, let's now come to the next, which is the properties of the vector spaces and dimensional vector spaces. So 1.4 properties of Rn, and we say this Rn is n-dimensional vector space. If we let U, vector U, vector V, and vector W, and the zero vector to be the elements of n-dimensional vector space Rn. And C and D to be the elements of real number. These are scalars. So I'll just give you the outline. So property number 1, U plus V. U plus V. If you add the vector A, U plus the vector V, it is the same as, it is similar to adding V plus U. So this is actually what we call commutativity. So they commute. So you can actually add U plus V, it is similar to V plus U. Number 2, U plus V plus W is the same as U plus V plus W. We can add like that. So you can add U plus V and then you add W, it is equals to U plus adding the V and W. So actually this is, I think this one is associativity. Number 3, if you add U plus zero vector, it is the same as, because zero vector is just 0, 0, 0. So it doesn't change. And that zero vector is actually the identity. That zero vector is the identity vector in the addition part. So you remember identity, right? Identity in the multiplication is what? Is 1, yes. In the addition is 0. And then number 3, U plus minus U is the same as 0 vector. Is the same as 0 vector. So you subtract the vector by its own negative, then you get the identity. The inverse of a negative is of a positive is a negative, right? Yeah. And then if you add the vector by its own inverse, then you get the identity. You get the identity. And then number 4, C plus U plus V. This is distributivity. So you're distributing the scalar. So it is similar to Cu plus Cv. You're distributing the scalar. Then number 5, if you have C plus D, and then you have the vector U. So here you are distributing the vector. It is similar to Cu plus Du. Then number 6, if we have C and then Du, then it is similar to just multiplying C and D, and then you multiply by the vector. And then finally, number 7, 1, 2, 3, 4, 5, 6, 7, and then finally number 8. If you multiply by the identity U, it is just similar to. And that one is just similar to 1. That is the identity. Okay, any question after that? Now let's come to number 2, the vector equation and linear systems. So in this section, then if we have like the equations that we had in the previous examples, we can write them in terms of the vectors, and then we solve them, And we start from definition 2.1. A vector equation in n dimension or in n variables, say x1, x2, all the way to x, let's say xp, is an equation of the form x1, a1, that is a vector, plus x2, a2, and that is a vector, plus all the way plus xp, ap, and this is equals to b, and this b are the constant terms, where a1, a2, these are vectors all the way to ap, and our b are elements are in the n-dimensional vector space. Now, the solution here, to get a solution here, actually the solution is just similar to the solution that you're getting in section 1. So the solution set is x1 equals to s1, x2 equals to s2, all the way to xp equals to sp. So this is actually the solution set. Okay, now let's look at example number 1. Example number 2 actually. Example number 2. show that x1 equals to 2 and x2 equals to 1 is a solution of the following vector equation. So this vector equation we write as x1 2, 3, 5 plus x2 -1, 2, and -3 equals 3, 8, and 7. So basically, this is A1, vector A1, and this one is vector A2, which is just like here. So we write it like that. So if the solution x1 is 2 and x2 is 1, then what is this? Is x1 and x2 the solution for this? So we can prove this. So we can prove. So when x1 equals 2 and x2 equals to 1, then 2, 3, and 5 plus 1, -1, 2, and -3 is equals to 1. So this is equals to 4, 6, and 10, and then plus -1, 2, and -3. Is this equals to 3? This one is 8, and that one is 7. Then it is equal, right? So it is equal. So it is proved. So it's proved. Now convert example number 3. Converts the following linear system to an equivalent vector equation. We have 4x1 plus x2 plus 3x3 equals to 9, x1 minus 7x2 minus 2x3 equals to 2, and 8x1 plus 6x2 minus 5x3 equals to 15. Convert this one to a vector equation. And our vector equation in this case will be, so the solution actually is, so we want to make this one to be like x1 a1 plus x2 a2 plus x3 a3 equals to b, So we want to make into that form. So in this case, then we can write this as, we can put this one in the brackets plus 4x1 plus x2 plus 3x3 x1 minus 7x2 minus 2x3, then 8x1 plus 6x2 minus 5x3 equals to what? Equals to 9, 2, and 15. Equals to 9. Then now we factor out those variables, x1 and x2. So we factor out x1 in the first one. Then when we factor out x1, then you remain with 4, 1, and 8. And then plus factor out x2, then we get 1 minus 7 and 6. And then plus we factor out x3, we get 3 minus 2 and minus 5. This equals to what? Equals to 9, 2. And that is our vector equation. Now it becomes now so easy to bring now these vector equations. You write this vector equation into the augmented matrix form. So therefore, in this case, our A1 equals to 4, 1, and 8. And this is actually our vector. Our A2 equals to 1 minus 7 and 6. And our A3 equals to 3 minus 2 and minus 5. And finally, our B equals to 9, 2, and 15. 9, 2, and 15. Okay. Then in this case, then we can write this in our augmented matrix form, whereby we can write this as 4, 1, and 8, 1 minus 7 and 6, and then 3 minus 2 and minus 5, and 9, 2, and 15. And therefore, this is the same as A1, A2, A3, and then what? Then B. Then B. And this is actually the augmented matrix of the linear. Any question up to that? So don't make a mistake. Get the comma. This is a matrix. The commas. It's A1, A2, A3, and B. So you're bringing together these vectors, and it becomes the augmented matrix. Now, you can go try this. Example 4 is simple. If you're told to convert now, convert the vector equations. X1, A1 plus X2, A2 plus X3, A3 equals to B. And the augmented matrix convert this one to an equivalent linear system, whereby we have our A1 to be equals to minus 2, 3, or A2 equals to 8, 5, and our A3 equals to 1 minus 6, and finally our B equals to 0, 0. So it's easy to convert this one to the linear system. So first of all, you write this form, and then now you separate. You distribute X inside there, and then it forms two linear systems. So what you form here will just be minus 2x1 plus 8x2 plus x3 equals to 0. The next one is 3x1 plus 5x2 minus 6x3 equals to 0. So this will be our linear system. Any question up to that? Okay, now. Now come to the third section here, and this is the linear combination of vectors. The linear combination of vectors. We'll start from 3.1, the definition. So an expression of the form C1 V1 plus C2 V2 plus CP VP, where V1 V2 all the way to VP are the elements of Rn, which is the n-dimensional vector space, and C1, C2, all the way to CP are elements of real number. These are the scalars. Is called a linear combination of the vectors V1, V2, all the way to VP with weights C1 all the way to CP. So when we add together the vectors, we multiply the constant or the scalar by the vector, and then we add together. Then it becomes the linear combination. Linear combination. The linear combination of the vectors. The linear combination. Okay, 3.2 subspaces of Rn. Subspaces of Rn. If we let V1, V2, and these are vectors all the way to VP to be the elements of Rn, then the sets of all linear combinations of V1 all the way to VP with weights in real number is called a subspace of Rn spanned by the vectors V1 all the way to VP, which you can write this as written as the span of V1, V2 all the way to VP, whereby this is equals to C1 V1 plus C2 V2 plus CP VP, whereby C1, C2, CP are elements of real number. So, real number. So spanning is still called generating the vectors. Generating the vectors. So the subspace is where you now take these vectors here and they actually generated from where this is the linear combination. So this is the linear combination where C1 and CP are elements of real number. So this R is, I think it's called generated in access. So it generated by first vector. Okay, so that is a subspace. So it's a linear set of all linear combinations of the vector spaces. Okay, now let's look at example number 5. Determine whether B, a vector B, is a linear combination of the vectors A1, A2, and A3, or not, where A1 equals to 1 minus 2 and 0, A2 equals to 0, 1, and 2, and then A3 equals to 5 minus 6 and 8, and then B equals to 2 minus 6, 2 minus 1, and 6. So determine whether B is a linear combination. It's a linear combination of B. So to determine whether this is a linear combination, then we want to see whether this will give us the what? The solution. We want to see whether it is actually consistent. So we want to see whether
I'm sorry, what is the middle term in that D?
-1. Yeah. So this is -1. So in this case, the solution here is that so what we want to do here, we want to get x1 a1 plus x2 a2 plus x3 a3 to be equals to what? To be equals to b. So we want to see whether that is equals to b. So therefore, we also want to see whether we can get the solutions here. We can get the values of x1, x2, x2, and x3. So those solutions, x1, x2, and x3 are actually our C1, C2, and C3. So they are actually our C1, C2, and C3. So then we need to write this in our augmented matrix form. So whereby we write 1, -2, and 0, and then 0, 1, and 2, 5, minus 6, and 8, and then finally 2, minus 1, and 6. 2 minus 1 and 6. Then we do what? Then we reduce this one completely. So when we reduce this, then when you go home and reduce this, what you get is 1, 0, 5, and 2, 0, 1, 4, and 3, and then lastly 0, 0. Now, since the last row that is not contradictory, then basically we get the solution. Basically, we get the solution. So it means that x1 a1 plus x2 a2 plus x3 a3 equals to b is consistent. Is consistent. Now, and then also, as you can see, since these are the pivot positions, the two of them here, then above the pivot position is already 0. So it is already reduced. So therefore, our new linear system here will now be x1 plus 5x3 equals to 2, we can start by looking at basic variable is equals to what? X1 and what? X2. Free variable is X3. Free variable is X3. Then X2 plus 4X3 equals to 3. So then X1 equals to 2 minus 5X3, and then X2 equals to 3 minus 4X3. 4X3. Then, therefore, X1 what am I doing here? Oh, yeah. So X1 equals to 2 minus 5X3. X2 equals to 3 minus 4X3. And our X3 is what? Is free variable. X3 is free variable. So X3 is free variable. So therefore, this one for what? For any X3. For any X3. Now, if we take X3 to be equal to 0, then X1 equals to 2 and X2 equals to what? Equals to 3. X2 equals to 3. So our B is equals to what? Is equals to X1 is 2, right? 2A, A1 plus what? Plus 3, A2, and then plus 0, A, 0, A. That is our vector. So our C is 2, and C2 is 3, and then C3 is. Any question up to there? Okay, so example, we still have 3 minutes. Example number 6. So determine whether B is a linear combination of columns in A where our A equals to 1, -2, -6, 0, 3, and 7, and 1, -2, and 5, and B equals to 11, -5, and 9. So this one, you do the same thing. This part already is written as, so this is just like the coefficient. So the same way, you need to put this one in augmented matrix form, whereby this will be 1, -2, -6, and 11, 0, 3, 7, and -5, and then 1, -2, 5, and 9. So once we reduce these, then what we get is 1, -2, -6, and 11, 0, 3, 7, -5, and then 0, 0, 11, and -2. Now, without even continuing from there, since you were just told to determine whether B is a linear combination of that. So since the last one, yes, it's not traffic, then it is what? It's so it's consistent. So you don't have to solve. for- So you are not told to find C1 the solution.
2,
Yeah, so you,
my last row,
you can.
0, 0, make 1, 2.
Yep, you can just switch, you can multiply by -1. Okay, any question up to that? So we can meet tomorrow. And then I have only one example and then we'll go to the next step. Okay, I'll see you guys tomorrow. Go and work on the worksheet.